Up until now, we have dealt with regression analysis, and our classical model of a simple regression model is this, where we explain the variation in the y variable with the variation in the x variable, and the slope here is then the causal effect of a change in y on a change in x on the change in y. So if x changes by, for example, 1 unit, then we would expect a beta 1 unit change in the y variable. We're going to use this framework to apply it on time series data. And we're going to use an example, which is the gross domestic product and how it grows. And gross domestic product, you remember that this is the value of all the goods and services produced in a country. But there are some new terms that we have to learn before we start with the time series analysis. Firstly, we have to look at how the data looks like, or what the data looks like. And this time series data is data for one entity, or the same entity, over multiple time periods. And here we have an example of quarterly GDP, gross domestic product, of the US economy. And we have data from 1962 to 2012, and in the data frame would look something like this. And you see that you have data points for every quarter. This is quarter 1, this is quarter 2, so there would be 4 quarters in 1 year. And you have the GDP as measured in billions of dollars. And what you would often do is that you would lag the data. So here, if you are, for example, in 1961, let's draw that a bit better. If you're here in 1961, the GDP is 30.99, and the first lag is the GDP in the last period. So these are equivalent to each other. Because in time series analysis, we often use lagged values to try to forecast new values. And this is, for example, the first lag. So this is for time t minus 1. And the third lag is then the value 3 periods ago, right? So you would often create lagged values, but you would also create differences. And these differences, they are just the value at time t. This is the first difference. This means that you take the value at time t minus the value at time t minus 1. So this would be 30.99 minus 30.78. So what you noticed from the table was that at a particular observation, yt is just indexed by the subscript t. This is quite practical because you can write yt to denote the value of y at time t, and then you can have the lagged value yt minus 1, which means the value of y in the period just prior to t, right? And the number of observations in a time series is often denoted by capital T. So you have t going from 1, 2, and so on until time capital T. We have mentioned lagged values, and yt minus 1 is often called the first lagged value or the first lag. And if you're looking, or if you're standing at a time period, for example, you have time here, and you have the y value here, and you have a counter 2, 3, 4, 5, 6, or 7, and so on. And let's see, I can write that a bit better. And these time instances can be days or hours or weeks or months or quarters or years. But if you're looking at time, or at the lagged value yt minus 1, you might have these values of y. But if you're looking at the lag, then if you're at period 4, then you should look at the y value for period t minus 1, which is period 4 minus 1, which means that you have to look at the value at time 3, right? So, and the t is just a counter, which means that yt minus 1 applies to all of the observations, right? So if you're looking at yt minus 1, or the observations, one lagged, then you see that you don't get a lag for the time 1 because you don't have data, right? You don't have data for it. And the value for time 7 is not a part of the lag, because maybe 7 is the end of your data structure, right? So, and you don't have to go one lag behind or only do the first lag. You can have lags of greater magnitude, and then you could talk about the yt minus j, which is the jth lag. This means that for every time period, you're looking j periods into the past to get the value of y. And I'm just going to clean up a bit the clutter. And you don't have to look into the past either. You can look into the future, which is the y of t plus j, which is the jth future value. And what you can do is, if you have this data structure of yt and the lagged value, then you can create the first difference, which is just the values subtracted, or the difference. So then you would get, for example, this is time period 7, then you would, in this case, get the difference between y7 and y6. So this would be the y value at time 7 minus the y value at time 6. But beware that you would, if you calculate the first difference, you always lose one observation, because the y in period 1 cannot be subtracted by the y in period 7 or 0, because this observation is not in your data set, which means that you would get a not a number. So you would get not a number, or you would get one less observation if you calculate the first difference. Often we use logarithmic form to investigate time series data, because think of the logarithm as the exponent to, for example, the base number e. So if we have e to the power of t, then our graph would look like, for example, this is y equals e to the power of t. Then this would be y, and we would see something like this, right? So this is time, and as time goes from 0 to 1, we have e to the power of 0, which is 1, right? And if we have 1 here, and 2, and 3, then we would see an exponential growth of this process. And often we add not the t alone, but we have to the r times t. Okay, so t is just counting the time periods, and r you can think of the interest rate. Okay, so then you would see this exponential exponential form of the y variable across time. And a lot of economic and financial processes, they are often modeled by this exponential process. Think of just your interest rate or your bank account. So this is the number or the amount of money that you have at time 0, and every single year you have more and more money in your bank account because of this exponential process. And when we take the logarithm of this, we are really just getting the exponent, right? And if you look at the exponent, then whenever you increase the t variable, 1, 2, 3, and so on, you increase the exponent linearly. So if you would like to, let's remove this, and if you have the logarithm of y here, then this graph would actually look something like this. It would be a linear function of time. And as you recall, a linear function, you can use a regression, ordinary least squares on this to find the, for example, slope and the intercept. right? So if you have a process, for example, a price or GDP, which grows, then you could just take the logarithm of the levels of the value of the GDP, and you could plot it against time, and you could run a linear regression. So you could try to do this with using, for example, a stock indices like S&P 500 and plot the data, take the logarithm of the index and plot it against time. And then you could fit a linear regression on that. And GDP, we expect GDP to grow exponentially because the foundation of GDP is really, or GDP growth is really that you increase, so GDP, because whenever you produce something in a country, some of what you produce goes back as investment. It's used to produce better roads, or better infrastructure, or more hospitals, or more production facilities. And this is called the capital. So every single year, you would like this capital to increase, and capital is not just money, it's actually stuff which is beneficial for the economy. And another factor behind GDP growth is increased productivity. And this means that every single person, or on average, every person in the economy, they produce more or more value per hour they work. This means that every single year you would expect, or over time, you would expect GDP to grow over time. Okay, so what if you take the difference, the first difference of the logarithm? So this is the first difference of the logarithm. So you have the y data, and you transfer it to the logarithm of y, and then you lag the y variable and take the difference. And what you could realize here is that by using the ordinary logarithm rules, the difference in the logarithms is equal to the ratio of the logarithms. Just try this with some numbers. For example, yt equals 10 and yt minus 1 equal 9, and you can check it. And this is equal to the logarithm of 1 plus the return of the y variable from period t minus 1 to period t, which is approximately equal to the first difference in the y variable divided by the y variable at t minus 1, which is the returns from t minus 1 to time t. Okay? So this approximation here, it's quite important to realize that this is only for small variations in y. So this only works when the returns are basically 1 percentage point or less, because this logarithmic what do you say, approximation, it really comes from continuous time finance and economics, in which you assume this process of y against time is continuous, like this. But in real life, you have certain time periods where you observe the process, and so if you have large swings here from one period to the next, then you should transform your data by using the ordinary yt minus yt minus 1 divided by yt minus 1, like the ordinary arithmetic return. But in our case, we use the logarithmic transform and the approximation. We are assuming that the difference in GDP is not varying a lot from time period to time period. And the if you would like to have the percentage change of the time series, you could just take the difference in log, the first difference in the logarithm, and times 100. So then you would get the change in percentage form. One of the benefits of working with logarithmic transformed variables is that it's quite easy to get the return for more than one period. So in this case, we have data on quarters. So this is 4 quarters in 1 year. We have the GDP in levels. We have the logarithmic transform of the GDP. And we have the change, the first difference of the logarithmic transform of GDP. So this is just 8.039 minus 8,032. So this is just the first difference of the logarithmic transform of GDP at time 1961 quarter 1 minus the logarithmic transform of y at 1960 quarter 4. And this means that if we use this, we take the difference, the first difference in the logarithm times 100 to get percentages, then we would get the logarithmic, or no, the returns for 1 quarter. But because we are working with logarithmic transforms, we can just take times 4 to get the estimated yearly equivalent of this change. And then in our case, we would get 2.8% increase in GDP on a yearly basis would be 4 times 100 times 0.007. So this is how you annualize the 1 quarter increase in GDP. What we often see in time series data is that the value of y in one period is correlated with either future values or previous values. And y is then said to be autocorrelated or serially correlated. And correlation and covariance, they are related, so we start with the autocovariance because this is a bit more easy to grasp and calculate. So the jth autocovariance of a series is just the covariance between yt and its jth lag. So we just write covariance between yt and yt minus j. So let's consider that you have your data like x1, x2, these are numbers, right? And xt, and you would like to figure out the one lag autocovariance, right? So you just compare this part to this part, right? So here you have xt minus 1, but what you do is that you compare these two tables. So you have x2 and x3 and so on until xt, right? Sorry. Okay. There we go. And we compare it to the data in this column, which has x1, x2 until xt minus 1. Okay? So what you have here is that you have data for time t and data for time t minus 1, right? So now you can just run the ordinary covariance function on these two columns in, for example, Excel. And probably some of you have noticed some sloppy notation, which we don't like. And this covariance between the yt and its jth lag is equal to this this equation. But the equation is such that this should either be an approximation, or let's see, I have to not erase everything, or it should have the t minus j minus 1, right? So this is to get the unbiased sample covariance or autocovariance between the yt value and the jth lag. And what you can do to understand these equations is just to just to make yourself an example. So here you have the covariance between yt and its jth lag, and you get the sample covariance, right? And this is equal to 1 divided by t minus, let's say that j equals to 1, right? So this is our example. So this would be 1 divided by t minus 2. And capital T, remember that this is the number of observations in your original data set, right? And you can then just take the sum from t equals 2, which is j equals 1 plus 1, times yt minus the average value of y from j plus 1, which is in our case 2 until t. And look at that, we have that column vector here from x2 to, or in our case, y. So it's just numbers here. And we have to times this with the yt minus 1 minus y hat, which is the average of the y variable for the observations from time equals 1 to time t minus 1. So, and we're going to do this in Stata, so we get a more tangible feel to it. But whenever you want to understand an equation, just put in numbers and make your own example of it. Now that we have the autocovariance, we can calculate the autocorrelation of a series. And this is just the autocovariance between yt and its jth leg divided by the sample variance of the yt variable. Just note that the variance here is for yt. And what this estimate of the sample autocorrelation relies on is that the variance of yt is equal to the variance of the lagged value. And because these are equal, we say that y as a process is stationary.